Yeah, good afternoon, students. Today we are going to discuss complex analysis. First, let me know what is that number system. Yeah, as we know that natural numbers, next to the whole numbers, the natural number will start with 1, 2, 3, so on, and that whole numbers will start with 0, 1, 2, 3, so on, and next rational numbers and integers. There is positive integer and negative integers. And the last one, we know that the real numbers. So real numbers means that all that including the natural number, whole number, rational number, and the integers. Okay. Now let us see that the complex numbers. So up to that in the 10th standards, we know that that real number is that biggest set in that number system. But actually, that the complex numbers, that is the biggest set in the number system. So what is the complex numbers means? So it is in the form of a plus or minus ib, and such that a comma b is belongs to that r. See what is the complex number set means? And every number that is in the form of a plus or minus ib, and where a comma b is belongs to that real number. So from this one we can say that the real number, the complex number set is the biggest set in that number system. Okay. So what is the I here? So that we can write the root minus 1. We know root 3 and root 5 and root 7 or whatever, root 2 minus 8. This all numbers is called what is it? Imaginary numbers. So that I we can say that root of minus 1. So suppose the root of minus 3, that we can write I root 3. And this is imaginary number. So this we can write 0 plus I root 3. So we can say that it is a complex numbers. Okay, did you understood about this one more? Next. So what is a complex number system is that? So this is the x-axis and this is the y-axis and this is the point z. So z equal to, we can say that x plus iy. Z equal to x plus iy. So here the x is called the real part of z. So thus we can write origin, that we can write real part of the z. And similarly that y thus we can say that imaginary number, imaginary part of z. Okay, that we can write that, and shortcut that we can write I am z. Okay, suppose z equal to, let's see, z equal to 2 plus or minus 5i. So 2 plus, sorry, z equal to 2 plus 5i. So here the 2 is called the real part of z, and the 5 is called the imaginary part of z. So here 2 is called the real part of the z and the phi is called that imaginary part of the z. Now, see the next one. Z equal to x plus iy. Okay, then the modulus of z, that we can write that mod z. So the modulus of z, that we can write the mod z, that equal to under root of x square plus y square. If z equal to x plus or minus iy, then the mod z equal to under root of x square plus y square. Now let's see that some example. Z equal to 5 plus or minus 3i. So 5 plus 3i or 5 minus 3, whatever maybe 5 plus 3i. Now let's take what is the modulus of z. So as per this one is what is that the mod of x square plus y square, no? So that here x equal to 5 and y equal to 3. Then x square, so that is become 5 square. So 5 square value is 25. And let us come to that y square. Y square value is 9. So therefore that we can say that 34. So this is that mod z value. That is called the modulus of z. And if z equal to x plus iy, then the z minus the augment matrix of argument of z, that is become component of z, also we can say the z bar. So z bar equal to x minus iy. Suppose z equal to x minus iy, then the z bar is become x plus iy. Let's see that one example. If z equal to 3 plus 4i, and z bar equal to become 3 minus 4i. Okay. And z equal to x plus iy, no? So from proper z bar is become x minus iy. So the properties of the complex numbers z plus z bar. So if you are adding these two, so what we are getting x plus iy plus x minus iy. So here that iy get cancelled and we are getting x plus x. So that is become 2x. And as we know that x is what is that the real part of this, so that we can say that the real part of the z. So z plus z bar equal to, we can say that z plus z bar equal to, we can say that the 2 into the real part of the z. And in the same thing, z minus z bar. So let us see that x plus iy and minus x and minus iy. Okay. So that is become plus iy. So x get cancelled, and here we get what is it? 2iy. So that's we can write 2i, the real part of, or the imaginary part. So here the what is the y one? So y equal to the imaginary part of the z. So this is the property of the properties of the complex number. So many is there one. And the one more thing, z into z bar. So what is a z into z bar? Let's see. X plus iy into x minus iy. So we know that z equal to x plus iy and the z bar equal to x minus iy. So z into z bar is become, that is become a plus b into a minus b. So a plus b into a minus b, nothing to what is that? A square minus b square. So thus we can get what is that? X square minus I square and y square. And we know that I equal to root of minus 1. And what about that I square is become -1. So if you are substituting that I square equal to -1, and that we are getting x square plus y square. So therefore, z into z bar equal to x square plus y square. So these are the some properties will be there. Okay. And one more thing, the argument of z, that we can say that a or z. So if z equal to x plus iy, then the augment of z is become that we can say that theta equal to tan inverse of x by y. So this is the property will be there. Okay. So let us do some problems about this one. Let's see some problems. So I will share the PDF. Just wait now and share the PDF. Is it visible? Sir, is it visible? The PDF? Yeah. So all the properties of the complex numbers, their associate law for additions. So Z1 plus Z2 plus Z3, Z1 plus of Z2 plus Z3 equal to Z1 plus Z2 plus Z3. Here Z1, Z2, here the Z1 and Z2 and Z3 are the three complex numbers. So the three complex numbers, and they are follow that associate property. Z1 plus Z2 plus Z3 equal to Z1 plus Z2 of Z. And that one more thing, inverse, that is multiplication inverse. Identity element. So let us come to that identity elements. And generally, we know that in the group theory, when we are studying in that UG level, and in the group theory, we have that identity element. With respect to addition, the identity element is 0. And with respect to multiplication, the identity element is 1. Okay. So with respect to addition, the identity element is 0. With respect to multiplication, the identity element is a 1. So in the same way, that identity element is we write as a 0. So 0, that is we can write 0 plus I into 0. So this is the identity element. So that we can z plus 0 equal to 0 plus z equal to z. And additive inverse. So when it's coming to the inverse, so in generally 2, what is the inverse of 2 with respect to addition, or addition inverse is become what is that? -2. So in the same way here, so z equal to x plus iy, know that minus z is also is there in the complex number, that is minus x and minus iy. So we can say that minus z is also inverse. So there is some properties and this commutative law. So that we can write that Z1 plus Z2 equal to, we can say that Z2 plus Z1. So up to here, this is with respect to addition, and from here, and this is with respect to multiplication. So addition, and here the multiplication property is there. Okay. Uh, Now let's see that next one. So here the some exercise problems is there, and we'll see what all is there. So find all the possible values of z and which are satisfying that z square equal to -9 and z square equal to minus k square. So if we know that z equal to x plus iy, no, so then the equation is become, let us see what will the equation is become, z square equal to -9. So z equal to x plus iy, no, so z square, so that is become, what is it, let us see here. So z square, that is become x plus iy whole square. So a plus b whole square formula. So that is become a square, okay, plus 2ab and plus b square. B square means iy whole square. So iy whole square, I square equal to minus y, no. So finally we are getting x square minus y square, x square minus y square plus 2xy equal to -9. So if you are comparing the both sides, if you are equating to the real part and imaginary part, so here the real part is x square minus y square, and here the real part is -9. So we can say that x square minus y square equal to -9. Okay. And next, one more. Here the imaginary part is on the left side is 2xy, and let us come to that right side. There is no imaginary part. So here we can write -9 plus 0 into I know. So here the right side point, what is the imaginary value? 0. So we can say that the 2xy equal to 0. So x square minus y square equal to -9 and 2xy equal to 0. So when you are coming to the 2xy equal to 0, so thus we can write that x equal to 0 or y equal to 0. Now if we have that y equal to 0, that is become x square minus y square equal to -9. So if we are substituting that y is here, and we are getting, what is that, x square equal to -9. So x square equal to -9, which is impossible. So we are not getting that here. And the other hand, so we can say x equal to 0. So if we are substituting that x equal to 0, and we are getting, what is that, minus y square equal to -9. So from there we can say that y equal to plus or minus 3. So y equal to plus or minus. So when it is x equal 0 and y equal to, we are getting plus or minus 3, and z equal to is become x plus iy, no. So y value is plus or minus 3, no, and x equal to 0. So completely we are getting z equal to plus or minus. And in the same thing, here the second problem, we can prove that the asterisk here in place of k square, here 9 is there, and we can prove that the same thing here. Let's see one next one. If n is a positive number, positive integers, and we have to prove that 1 minus z power of n by 1 minus z equal to 1 plus z square plus so on plus z power of n minus 1. And the second thing is also there. So first let us prove that. Let's take p of z equal to, let's take the right side part. 1 plus z square plus so on z power of n minus 1, and where z is z is not equal to minus 1. And from there we can say that p of z minus z into p of z. Let us see what will happen. See there, p of z minus z into p of z. So z into p of z means, so we have to multiply with z is on all sides. So when you are multiplying with the last part into z, z power of n minus 1 into z. So that is become z power of n. So p of z minus z into p of z equal to 1 minus z power of n. So from there we can write that p of z equal to, when you are taking the p of z is common, so we are getting 1 minus z. So 1 minus z into p of z and equal to 1 minus z power of n. So p of z equal to 1 minus z power of n by 1 minus z. So this is the theorem. And next to come to the second one. Same, if w is not equal 0 and z is not equal to w, and then w by z is not equal to 1. So in that, substitute that z by w for z in the equation 1. So from here, so then we are getting 1 minus z. So from there we can say that z power of n minus z power of n by w minus z. And we are getting the same thing. Just we are substituting z by w. Now, see, the third problem is there. So express each of the following numbers in the form a plus ib, where a comma b are the real numbers. So we have to simplification and we have to do the rationalized here. 1 minus I, 1 minus I by 1 plus I. See the, let's see the first problem. 1 minus I by 1 plus I. So if you are doing the ratio like that, 1 minus I by 1 plus I into 1 plus I by 1 plus I. So 1 minus I into 1 plus I, that is a minus b into a plus b, that we can say that a square minus b square. Otherwise here, same thing, 1 minus I, if you are multiply with 1 minus I by 1 minus I, numerator and denominator. So that has become 1 minus I whole square by 1 plus I into 1 minus I. So 1 minus I whole square. So a minus b whole square. So when you are expanding this one, so what we are getting? A square minus b square minus 2ab. So 1 minus 1 square, and finally we are getting the 2i. Next, 1 plus I into 1 minus I. In the, let's see the denominator. 1 plus I into 1 minus I. In that, generally a plus b into a minus b, that we can write that a square minus b square. But a plus ib into a minus ib, that we can write that a square plus b square. So in the same way, 1 plus I into 1 minus I, that we can write that 1 plus 1. So that we can write that 2. And see the next one, 6 plus I by 7 plus 3a. So we are doing that, rationalize the denominator, that we can write 6 plus I into 7 minus 3a by, and in the down we are getting 7 plus 3i into 7 minus 3i. A plus b into a minus b. A plus, thus we can write as in the complex number a square plus b square. So a square is the 49 and the b square is the 9. Understood? So for that we are getting that 58. So now see that in the numerator. So if you are multiply with 6 sevens are 42 and 6 threes are 18 and I into 7 is 7i and finally I into 3i plus into minus minus. So I into 3i. So that is become minus I square minus 3i square. So minus into minus plus. So that's we can get 42 here minus 18i plus 7i, that is become minus 11i, and here minus I into 3i, so that is become plus 3. So that we can finally we are getting 45 minus 3i. So in the numerator, and let us come to the denominator, and that we are getting to the 58. Okay. And next, so show that for any complex number z and w, real part of z equal to z plus z bar by 2 and imaginary part of z equal to z minus z bar by 2y. Let us see the first one. And z equal to x plus iy, then the z bar is become x minus iy. So when you are adding the both z plus z bar by 2 and here iy get cancelled and we are getting 2x by 2. So 2 get cancelled and we are getting x. So x is nothing to what is the real part of the z. And next one here, z minus z bar by 2y. So when you're doing the minus, that xx get cancelled and we are getting iy plus iy by 2. So that is become 2iy by 2y. So 2y get cancelled and we are getting y. So y equal is nothing to real part of the z. And z plus w bar, whole bar, z plus w whole bar. So z equal to x plus iy and plus w equal to this u plus iv. So here one more the function is that the w. So w equal to u of I plus v. Okay. Let us see that from there we can write the real part and imaginary part. That is we can get x plus u plus y plus v. I into y plus v. Here the real part is become x plus u and the imaginary part is become y plus v. So when you are doing the bar x plus u minus I into y plus v. So again substitute that, write the imaginary part and real part. So x plus minus iy is one side and u minus iv. So x minus iy, that's we can write the z bar, and u minus iv, that's we can write the w bar. So that is a prove that z plus w whole bar equal to z bar plus w bar. And next one, z into w bar. So what will say that? So in the same way, z we can write that x plus iy and w we can write that u plus iv. So when you're doing the multiplication and write real number and imaginary number, that we can write the xu minus yv plus I into yu plus xv. So thus we can write real and bar, so that we can write the minus. So xu minus yv minus I into yu plus x. And again, if we are write separately, x minus iy into y minus iv. So thus we can write that z bar into w bar. So this is the mode of zw bar. And finally, let's see that mod z, mod z bar. Let us see here that first z equal to x plus iy, and that mod z bar is become x minus iy, and they are asking to the mod z bar, so that is become under root of x square plus minus y whole square. So that has become mod of x square plus y square. So mod of x square plus y square is nothing to that mod z. So from there we can say that what is it? Mod of z bar equal to mod z. So this is the concept. And next, the mod of z bar. So x minus iy, again that mod x minus iy, again we can say that x plus iy, z bar and whole bar. So again we are getting that z, and this is the some properties of the complex numbers. Yeah. Now, how we can find the root of the complex numbers? Generally, if they are giving the equations, we can find that roots either using that quadratic equation we are using minus b plus or minus b square minus 4ac by 2a. In any equation we can find all that. Now, if we are, how we can find that nth roots of the complex numbers? Okay. What are the cube roots of the unity? What is the cube roots of unity? Generally, we know that 1 omega omega square. Suppose that x cube equal to 1, and what are the cube roots of unity? That 1 omega omega square. And what are the fourth roots of unity? So that's we can say that 1 minus 1 and I minus I. 1 minus 1 I and minus I. So these are the fourth roots of unity. So now here they're asking to find that nth roots of unity. Okay. Now writing the complex number in polar form and very easy to solve that equation. So R equal to f of t, it is a polar form. Let us see that. Let's see that z power of n equal to a, and where a is a non-zero complex number and n is a positive integers. So already we proved that something. What is that? Mod of z power of n equal to mod z power of n. Okay. So here theta, what is that theta? The argument of the z, and then n theta is also become that argument z of z power of n. So let us see that how we can solve that roots means the solution of z power of n is equal to a in the solution of z power of n equal to a are called what is the nth roots of the a. So they're asking to that nth roots of the a. A is a what is it? Is non-zero complex numbers. The solution of the z power of n equal to a, we can say that nth roots of the a. So let us write a equal to rho of cos pi plus I sin pi, and z equal to, this is the polar form, r into cos theta plus I into sin theta. So r equal to under root of x square plus y square. Here is the now they given that z power of n equal to a, no. So from there, in place of z, substitute r into r of cos theta plus I sin theta. So that is become r power of n. And when we are using the binomial theorem, cos theta plus I into sin theta whole power of n. So thus we can write that cos n theta plus I into sin n theta. So if we are substituting there, and we are getting r power of n of cos n theta plus I sin n theta. Now come to that a. What is the a value? That rho into cos pi plus I sin pi. Now let us equate to both side imaginary part and the real part, and we are getting r power of n cos n theta equal to rho into cos pi, and r power of n cos n theta equal to rho into sin phi. So from there we can say that r power of n equal to rho cos n theta equal to cos pi, and sin n theta equal to sin pi. So it is from there clearly we can write that r power of n equal to rho and n theta equal to pi. So from there r power of n equal to rho. So from we can write that r equal to rho power of 1 by n. So that is we can write that nth root of the row. So this is a solution of the nth roots of the complex number. So depending on this method, and we are solving that, and we are finding that nth roots of the complex numbers. Yeah. See, the solution of the z power of 4 plus 1 plus I. Okay. So 1 plus I. So when you are writing to the complex numbers, when you are writing in the polar numbers, multiply and divided by root 2. So that is become 1 plus I. So I am multiplication and divided by root 2. So that is become root 2 into 1 by root 2 plus I into 1 by root 2. So 1 by root 2, that is we can write cos 45. So cos 45 we can write that cos pi by 4, and similarly that 1 by root 2 again we can write sin pi by 4. So 1 plus I we can write that root 2 into cos pi by 4 plus I into sin pi by 4. So how we can get means we are dividing and multiplied by root 2 on both sides. So 1 by root 2, that's we can write cos pi by 4. Again 1 by root 2, that's we can write that sin pi by 4. Okay. Then the fourth roots of 1 plus I. So just now we say that is become r power of n. So already here that is root 2 is there. Root 2 and whole power of 1 by 4. Root 2 that we can write 2 power of 1 by 2, and that we can write 1 by 4. So completely we are getting 2 power of 1 by 8. So 2 power of 1 by 8. And here this is all power of n. Here n means what is that? 4. So cos pi by 4 plus I sin by 5 whole power of 4. So as per the binomial theorem, that we can write cos pi by 16 plus I sin pi by 16. Hence the all the fourth roots of root of 1 plus I given by. So finally we can write that 2 power of 1 by 8 cos pi by 16 plus k pi by 2 plus I sin pi by 16 plus k pi by 2. So we need the four roots, na? So for the k value of 0, 1, 2, 3. So if we are substituting k equal to 0, we are getting one root, and k equal to 1, one more root, and k equal to 2, one more root, and k equal to 3, one more. So these all four roots we are getting. So that is the solution of the z power of 4 equal to 1 plus I. And next, find all the values of z, which is z power of 5 equal to minus 32. So minus 32. So when you're writing 32 is outside, minus 32, we can write that 32 into minus 1. So minus 1, we can write that cos pi plus I sin pi. So that we can write 32 into cos pi plus 2k pi plus I sin pi plus 2k pi, and where k equal to 0, 1, 2, 3. And now z power of 5. So z power of 5 means that is become 2 power of 5 cos 2k pi plus I sin 5 plus 2k pi. So therefore z equal to become whole power of 1 by 5. 32 we can write what is the 2 power of 5. So that we can write 2 power of 5 whole power of 1 by 5, and cos pi plus 2k pi plus I sin pi plus 2k pi whole power of 1 by 5. So here 2 power of 5 5 get 2 power of 5 is there, no 5 5 get cancelled, and we are getting the 2, and here cos pi 2k 5 by 5 plus I sin 5 plus 2k plus 1 by 5. So when you are substituting k equal to 0, 1, 2, 3, 4, so that are the solution of the z power of 5 equal to minus 32. When it is, here we have to substitute k equal 0, we are getting one solution, and k equal to 1, we are getting one more solution, and k equal to 2, we are getting one more solution, and 3, 4 also we are. So all 5 solutions are solutions of the z power of 5 equal to minus 32. And next to find all the solution of z power of 4 plus z square plus 1 equal to 0. So consider the identity that we can say that z power of 6 minus 1. So that's we can write that z square minus 1 into z power of 4 plus z square plus 1. Now see that z power of 4 plus z square plus 1 equals 0, and from the deleting the solution z equal to plus or minus 1, or z square minus 1 equals 0, and the solution are become z power of 6 equal to 0. Z power of 6 minus 1 equal to 0. So from there z power of 6 minus 1 equal to 0, or from there we can write z power of 6 equal to 1. So 1 we can write that cos 2k pi plus I sin 2k pi. So z equal to, we can write that cos 2k pi plus I into sin 2k pi. So now we are writing whole power of 1 by 6, no? So that is become z equal to cos 2k pi by 6 plus I sin 2k pi by 6, and where k value is become 0, 1, 2, 3, 4, 5. But z equal to plus or minus corresponding to the given values when you are substituting k equal to 0 and k equal to 3. So when you are substituting k equal 0, that is become cos 0 and I sin 0. So we are getting that is z equal to plus or minus 1. And when you are substituting that k equal to 3, so when you are substituting k equal to 3, that is 6 pi by 6. 6 6 get cancelled, and we are getting cos pi. So that is plus or minus 1. So the remaining solutions are z power of 4 plus z square plus 1 equal 0 as given by z equal to cos k pi by 3 plus I sin k pi by 3, when we are substituting that k equal to 1, 2, 4, and 5. So for 0 and 3, we are getting the solution of z power of 6 minus 1, no? And when the remaining are 1, 2, 4, 5. So z equal to cos of k pi by 3 plus I sin k pi by 3, and k equal to 1, 2, 3, 4, and 5. So this is the solutions of the z power of 4 plus z square plus 1 equal to 0. As we know, just now we discussed z equal to x plus iy, and then the number z minus iy is called the conjugate of the z, and we can write that z bar equal to x minus iy. Yeah. So here some problems are there. Find the mod z and the argument of the z. So we need to find that mod z and that argument of the z. Okay. See, let us see mod z, and we know that the mod z value mod z equal to z equal to x plus iy, and that mod z equal to become under root of x square plus y square. So here the first problem is there, z equal to minus I. Z equal to minus I. So that we can write that z equal to 0 minus I. So when you are comparing with z equal to x plus iy, then x is become 0 and y is become minus 1. So what is the mod z is become under root of x square plus y square. So that is become under root of 0 plus 1. So that is become 1. So we can say the answer is mod z equal to 1. And next, argument of z. So that is become theta, that is become tan inverse of y by x. Then the theta equal to tan inverse of y by x. Now here the question is z equal to minus I, know. Compare with z equal to x plus iy, and that x is become 0 and y is become minus 1. Okay. Now let us see there. What is the theta equal to tan inverse of y by x? So the theta equal to tan inverse of y by x, no? Then theta is become tan inverse of y by x. So y is minus 1 by 0, and that we can write minus tan inverse of minus 1 by 0. That is infinity. So when we are getting the infinity, pi by 2, tan pi by 2. So that is equal to minus tan inverse of tan pi by 2. Tan get cancel, and we are getting theta equal to minus pi by 2. That argument of z equal to minus pi by 2. And this is the how we can find that the solution. Okay. Now let's see the one more problem is there. No? Z equal to minus root 3 and minus I. Z equal to minus root 3 and minus I. Now here x value is the minus root 3 and y value is become minus 1. So first he is asking to find that mod z. So the mod z equal to, we know that under root of x square plus y square. So that x square is become root 3 whole square, that is become 3, and y value is minus 1, no, that we are getting 1. So that root 4. So the root 4 value is 2. So therefore, we can say that mod z equal to root 2. Next, they are asking to find that argument of z, no? That is tan inverse of y by x. So the tan inverse of y is what is that? 1 minus 1. And here this is become root. So tan inverse of 1 by root. Is anybody know what tan inverse of 1 by root 3 value? What is a tan ma? Is there some Anugish? What is a tan? Tan theta.
Tan 30, sir.
Yeah, tan 30. Tan 30 we can write what is a ma? 5 by 6. Yes, na?
Yes, sir.
So that we can say that tan 5 by 6. That both are get cancelled and we are getting 5 by 6. But here, observe one thing, ma. When x and y values, so both are negative. So this is the coordinate. Here x and y value both are negative. That is will be in the third coordinate, na? So when you are taking x-axis and y-axis, so both are negative, then the argument values become phi minus theta minus phi. What are the value we are getting? Theta minus phi. So here we get the theta value is pi by 6, no? So pi by 6 minus pi. So that is become pi minus 6 pi by 6. So pi minus 6 pi is nothing to minus 5 by 6. So this is the value of the argument of z. So mod z and argument of the z. So you can also find out that the remaining problems more. Fourth one and fifth one. So just the mod z equal to under root of x square plus y square, and next argument of z equal to that equal to theta equal to tan inverse of y by x. So these are the uh, important about that formulas. Mod z equal to under root of x square plus y square, and the argument of z equal to theta equal to tan inverse of y by 6. Okay, ma? Okay, ma, is it clear? And next, the limits and continuity. So this the picture was not good, ma. So we'll continue this class is next Saturday. Okay, ma. So here the limits and continuity, just I will give the explanation about to the limit. So when you are studying in the sequence and series, so what is the limit means? Limit Sn equal to L, that we can write that the mod of Sn minus L is less than to epsilon for all n is greater than or equal to m. Then we can say that the limit of Sn equal to, we can say that L. So in the same way here, here also we can find out the limits and continuity in the same definition when we are using the real analysis, and that the same definition is also coming here.